Hello, this is Senior Design Team 2, working with the FDA, and our project is on mapping defibrillation pulse attenuation. Group members include Justina, Pennala, Morgan Reamer, Ian Sousa, and Emily Vitale. Our problem statement. The current standard creates an issue of over-engineering for some medical devices, which can prevent products from reaching the market on time and result in higher engineering prices. While the 5 kilovolt defibrillator voltage may be appropriate for medical devices with applied parts within the vicinity of defibrillator pads, it is unnecessarily high for medical devices with applied parts outside the patient's thorax area, as they will not experience the full strength of the pulse wave due to bodily attenuation. Some examples would include an electrocardiogram, electroencephalogram, pulse oximeter, surface electrodes at distal points in the body, and some cochlear implants. Our solution statement. We wanted to design a human impedance simulation model to provide an accurate representation of the attenuated defibrillation strengths at locations on the body. Some of the factors that may affect electrical attenuation would be BMI, defibrillation voltage, the voltage that the patient is actually being defibrillated at, as this can change depending on the doctor's discretion, height and weight of the patient, and internal versus external components of the devices themselves. So some of the methods we went about designing this, we designed what our requirements would be, which we wanted to study an average adult male. We wanted it to be external defibrillation as opposed to internal with some of the IEDs that are invented. We wanted to work with external medical devices that aren't implanted into the patient. And we wanted to study the magnitude of the electrical field at certain points on the body. So to do this, we attempted to make an ANSYS computer simulation to be able to measure the electrical field at certain points in the body. And we also tried using an electrical circuit model. Both of these ran into their own problems. The ANSYS computer simulation, the geometries would not mesh and not provide us with any useful data. And the electrical circuit model was a little bit too simplistic to actually simulate the complexities of a human body. Now, for what we actually ended up working with was an extended physical model, which we hopefully someday will be able to work into a full body physical model to study the human body's electrical attenuation. So some of the final results we got from our experiments, this here is our tray experiment where we put 2 electrodes, you can see in black on there, in a solution which was contained within a tray. And we studied the electrical field at different points distal to the current path. And you can see there, as you get farther away, you experience less voltage, ultimately. In conclusion, the relationship between applied voltage and measured voltage is a linear, indicating that experiments can be conducted at lower voltages and extrapolated to defibrillation voltages, which is very useful for research into this subject. At greater distances from the applied voltage, there was less measured voltage, indicating that pulse attenuation occurs at distance away from the voltage pulse increases. The experiment results map defibrillation pulse attenuation in the physical models, showing that devices distal from a point of powerful electrical application, defibrillation, will not experience the entirety of the pulse, but a percentage of it. Some future work we hope can be put into this subject. Using a computer simulation model validated by our experiments could be conducted. This would allow researchers to have insight into the electrical attenuation of the human body without actually having to use the human body, as they are difficult to source, and there are a lot of legal issues, not to mention ethical issues with doing so. The use of animal testing, such as pigs or large mammals, at a low voltage to see the difference but also prevent harm to the animal could be employed to provide a more accurate living model. Cadaver testing using defibrillators and measuring probes at key locations can provide the most accurate non-living physical model. And some acknowledgments for those that worked with us, Dr. Soykan, Dr. Jingfeng, Jiang, Mr. Hamid Godes, and Dr. Standing Weininger. Both of those are from the FDA. Thank you.